All right, this video is going to briefly go over some of the highlights of the Mr. Freeland and Mr. Curtis problem that you worked on in class while the sub was here. Seems like this document's tweaking. It's like vibrating. It's pretty cool. All right, so here we go. Mr. Freeland and Mr. Curtis have a bet. There's two classes. Freeland has 40 total students, actually 30. Curtis has 40. The bet is that Mr. Freeland gets more students that get A's or B's than Mr. Curtis, even though Mr. Freeland has less students. So what you should recognize is that the number of students that each teacher gets that gets an A or B, those are binomial random variables. Okay, so you already have the solution, so I'm going to go through that really quick. So I've got these two random variables. The number of students in Curtis's class that get A's or B's, the number of students in Freeland's class that get A's or B's, those are binomial. Okay, so those are the parameters of the two binomial models. The probability we want is right here. We want the probability that Mr. Freeland outscores in terms of number of students with A's or B's Mr. Curtis. Okay? Now, if we use two binomial models, this is going to be a hard problem. However, we might see if a normal approximation will be reasonably accurate for both binomial models. And first thing is I found the means and the standard deviations of each random variable, the binomial random variable. And then we are checking to see if a normal model is a good approximation. This is a necessary step. We must show that n times p and n times 1 minus p are greater than or equal to 10 for each of the binomial models we're talking about. We must justify in a normal approximation. That's something we haven't necessarily talked about too much in class, but that's a really important thing that we have to do. Okay, so in these cases, n times p and n times 1 minus p are greater than 10. So I can use normal models and be reasonably accurate for the two binomial random variables that we're talking about. Okay? Well, since the probability we want is really the probability that f minus c is greater than 0, we can look at the mean and the standard deviation of the difference. Okay? So I expect Mr. Freeland to have 1.5 students more score than Mr. Curtis. Okay? To find the standard deviation, we add the variances, okay, from the two normal models that we found here. Okay, process we've done many times, and then I'm going to find the probability that the difference we got is greater than 0. Well, here's the expected difference. Here's 0. I'm finding the area under the curve here. I find a z-score, and I use normal CDF to see if there's about a 65% chance that Mr. Freeland's has more students that gets A's or B's than Mr. Curtis, which was the bet. Okay? Fairly straightforward problem. We're using normal approximations of binomial because it makes the problem so easy. Okay? All right. On the back, very similar question in that we have two binomial models. We have the number of multiple choice questions that are correct, and we have the number of true-false questions being correct. Those are both binomial models. And we're interested in the sum of those being greater than 45. Okay? So I'm going to do the exact same process that we did on the front of the sheet. I'm going to find the means and the standard deviations of each of those random variables. Again, very important step. We're going to check to see if a normal model is reasonable in both cases. And for both, they are. And again, that rule of thumb is that NP is greater than 10 and n times 1 minus p is greater than 10. Okay, that's the rule of thumb that says a normal model will work reasonably well. It is met in this case. Now, I want to emphasize one thing. This is not n times 1 minus p. All right, it's the expected number of failures, not the standard deviation. The standard deviation NP here. This is n times. We're just noting that because I've noticed that people do that sometimes. Same process as before, except we're not using the difference, we're using the sum. So to find the mean of the sum, I find the mean of x and add it to the mean of y. So 15 plus 25 is 40, but I still add the variances just like I did when I was taking the difference. Okay? So we see the mean and the standard deviation of the difference. That's approximately normal because we're adding two normal models. I draw the probability I'm trying to find the z-score and so forth, and we see that there's about a 20% chance of passing the test just by pure luck. Okay? So these two problems are very similar. One of them deals with a difference. Okay, that would be the Curtis-Freeland problem. And one of them deals with a sum. However, we approach them in the same way. It's very difficult to combine two discrete random variables that have many, many different outcomes. So we say, let's use a normal approximation. We check to see if that normal approximation is reasonable, and we combine the random variables, assuming that they're normal, to get an estimate of the probability that we want. Okay, so two kind of harder problems that you are expected to be able to do. So please use these videos as a resource, back them up, slow them down, do whatever you need to do to understand these types of problems.